Now, let's look at the last three examples in part 3. Here's an example, an interesting one. In the figure here, O is the center of the circle. You can see that. OQ bisects LP. OQ bisects LP at K. Therefore, this bisects that at K. Now, LQ and PQ are tangents at L and P, respectively. Obviously, LQ is a tangent at L and PQ is a tangent at P. Now, LQ is equals to 12 units. LQ 12 units, you can see that. And MQ is equals to MQ, this part, only from here to there, it's 8 units. And angle P is 53. You can see there that angle P is 53. Now, they say to us, name with reasons two angles which are equals to 90. We can put that as our A. They say, name with reasons two angles which are equals to 90. Before we can start with solving this problem, we know now we have a culture in geometry that we must first eliminate all the theorems which are not in this problem. Now, if we are used to that culture, then it will be easy for us to solve problems, because we are going to be left with theorems which are in the problem, and we are also going to we can use part 1 to also solve this problem, together with theorems which are left in this problem. Now, are there chords? We are eliminating theorems. Are there chords? Yes. Most times there are chords. Are there chords? Yes. Are there cyclic chords? They never talked of any cyclic chords in the story that I've just read now. Are there tangents? Yes, there are tangents, because LQ and PQ are tangents. Therefore, we don't have theorems of cyclic chords. We take those out. So we now eliminate theorems on chords. Now, is there a line from the center to the midpoint of the chord? Since we were told that OQ bisect LP, it means that LK is equals to KP. We know by bisecting, it means that it divides the line into two equal halves. Therefore, OQ divides LP into two equal halves. Therefore, we can see that this LK is equals to KP. Now, there is theorem number 1, because there is a line from the center to the midpoint, because it bisects LP, this line. Therefore, theorem number 1 is there. Now, is there angle at the center 2 times angle at the circumference? No. You might be tempted to say this angle is 2 times that angle. Don't be tempted. This must be in the circle for us to say this is 2 times that. Therefore, there's no theorem number 2 here. Is there theorem number 3? There's no diameter. We are not told about any diameter. No theorem number 3. Is there angles at the same segment? No angles at the same segment. You can be tempted to say that this angle is equals to that angle, which is not, because this line is outside. This is the tangent. It's outside the circle. Therefore, this cannot be equals to that. We cannot have angles at the same segment. Now, we don't have theorem number 4. Therefore, we only have theorem number 1. Cyclic chords, we have just said it, that they're out. Theorem number 5 and 6 are out. Now, do we have theorem number 8 on tangents? Now, we're on tangents. Do we have theorem number 7 first? Theorem number 7, a line drawn from the radius is perpendicular to, yes, there is, because there's the radius which is perpendicular to the tangent. Therefore, theorem number 7 is there, T7. Because we do have a radius and a tangent Therefore, they are perpendicular. That's what we know. Already, as you are eliminating theorems, already you are solving this problem indirectly. You are solving this problem indirectly. Now, is that theorem number 8? Yes, there is. There are tangents from the same points, because these are two tangents from the same point Q. Therefore, theorem number 8 is there. Theorem number 8 is there. Is there theorem number 9 here? There's no theorem number 9 here. Why? Because there's no angle, which is, yes, there is an angle made by the chord and the tangent, but this angle there, it's outside the circle. Therefore, it cannot be in the alternate segment, whether this makes an angle with this chord and this angle is subtended by the chord. There's no way that this angle is in the alternate segment because it is outside the circle. Therefore, we don't have theorem number 9. Therefore, we only have theorem number 1, 7, and 8 in this problem. Now, A, name with reasons two angles which are equals to 90. They want us to name with reasons two angles equals to 90. One thing that I'm sure of is that this and this are perpendicular, because this is the radius which is perpendicular to the tangent, of which we've just said that there is theorem number 7 here. Therefore, the radius is perpendicular to the tangent. Therefore, this is 90. Oh, therefore, angle L1, angle L2 is equals to 90 degrees. Reason, radius or tangent, perpendicular to the radius. Or radius perpendicular to the tangent, however we prefer. Therefore, this is the first angle, which is equals to 90 degrees. Another angle, because they said name with reasons two angles which are equals to 90 degrees. This is the first angle. This angle plus this angle is the same as Q angle LO. Therefore, that is why I can just put it like that. Now, another angle that is equals to 90, I'm still on A. Obviously, theorem number 1, we've just said it, that it is in this problem. Therefore, there is a line from the center to the midpoint, because we were told that OQ bisects LP. If it bisects LP, it means that OQ cuts LP into two equal halves. Therefore, it means that there is a line from the center to the midpoint of the chord, which means that this is 90 degrees there. If a line is drawn from the center to the midpoint of the chord, then that line is perpendicular to the chord. Therefore, O angle K, P. O angle K, P is equals to 90 degrees. Why? Because we've just said it, that theorem number 1, line from center to the midpoint, line from center to the midpoint of the chord. Line from center to the midpoint of the chord, I can mention which chord is that, LP. But no need, because at this point I can see only one chord here. Now, line from the center to the midpoint of the chord, that's what makes O angle KP to be 90 degrees. Prove by calculations that L angle OQ is 53. Then they want us to prove that this angle here is a 53. Now, for us to prove that this angle is a 53, which is L angle OQ, which they want us to prove that it is 53, now we start by saying, all right, this angle, which is L1, but before I can talk about the angle L1, I have to talk about this to be equals to that. Theorem number 8, don't forget that tangents from the same point have equal lengths. Therefore, tangents from the same points have equal lengths. From the same point, which is Q. Therefore, they've got equal length. Therefore, LQ is equals to QP. LQ is equals to PQ. Risen tangents from the same point. We know they have equal lengths. Tangents from the same point, we know they've got equal lengths. Now, angle L1 is equals to angle P, which is equals to 53 degrees. Risen, we know these are base angles of isosceles triangle LQP. Why are they base angles of an isosceles triangle LQP? Because LQ is equals to QP. Now, we know that this angle is 53 because it is equals to angle P. Now we are going to use this to calculate this angle there. We are going to use this to calculate this angle there. We know that this angle there is 90. We've just said it. This angle is 90. We've just said it. Now, we are going to calculate this angle using this. I'm going to write it here. Angle L1 plus angle L2 is equals to 90 degrees. I want angle 2. Angle L2 is equals to 90 degrees minus angle L1. Now, angle L2 is equals to 90 degrees. We know angle L1 is 53 minus 53, which is equals to 37 degrees. Now, we know that this angle here is 37 degrees. We know that this angle here is 90, as we have said there, that O angle KP is 90 degrees. Therefore, this angle outside here is equals to this angle plus that angle there. Is equals to this angle. We know exterior angle of a triangle is equals to the sum of the opposite interior angles. Therefore, O angle KP is equals to angle L2 plus L angle OK, or L angle OQ. Now, risen, this angle is equals to this angle plus that angle. Exterior angle, because this angle is outside this triangle there. Exterior angle of triangle KOL is equals to sum of opposite interior angles. Exterior angle of triangle KOL, which is KOL, is equals to the sum of opposite interior angles. Now we know that this is 90, as we have said it there, 90 degrees, which is equals to, we are proving that L angle OQ, don't forget, it is equals to 53. Now we know L2, and L2, it is 37 degrees plus L angle OQ. Now I take this to the other side. Therefore, we have, I just want to erase here because we now understand what is happening there. Now, we know if you take there, we're going to have 90 minus 37 degrees, which is equals to L angle O Q. L angle O Q, this is Q, is equal to 90 minus 37 is 53 degrees. We have proved that this angle here is 53 degrees. Now, C, we are told in C that we must calculate the length of the radius of the circle. We must calculate the length of the radius of the circle. I just want to go back somewhere there. Oh, from here, obviously, we should have, if we wanted, we could have given a reason that from A, because this is what we calculated from A. This is what we calculated from A. And we gave a reason that the radius is perpendicular to the tangent at the point of contact. Therefore, that is why I said we use this that we've done at A to calculate L2. Then after we show that L angle OQ is 53. Now, I want us to do C. With C, they say we must find the length of the radius. This is an example of a question where trigonometry does not work. I think I once promised in the previous examples that there are examples where the trigonometric ratios cannot work in a geometric problem. Because here, the longest side of the right angle LQO, the longest side, which is the hypotenuse of triangle LQO, the hypotenuse, it is MQ to be 8. So we are not given the whole OQ. We are only given MQ. So we can't use trigonometric ratios where we'll use opposite over adjacent to get our radius, because we know that our hypotenuse and this triangle, which is LQO, we have only MQ. We don't have the whole OQ. Therefore, we can use trigonometric ratios to find the radius. Where we're going to say adjacent, where we're going to say we can't use this. I just want us to be, we can't use this. This angle we know is 53. We can use opposite over adjacent, which is tan 53 degrees, which is equals to opposite, which is LQ. LQ over LO. LO, sorry, LO. Let me just fix that. LO. Now, for us to find LO, this is going to be over 1. This multiplied by that is going to be LO tan 53 degrees, which is equals to this times that is LQ. Now, we want, no, I'm still showing you that we can use trigonometric ratios here in this problem. Yes, in other problems, as you have seen, we could use trigonometric ratios, but here I did give a specific reason why we can't, because our OQ is given as MQ to be 8. We are not given the whole of OQ. Now, for us to solve LO, which is our radius, obviously we're going to divide there by tan 53 by tan 53. Now, obviously that will cancel. LO, which is equals to R, which is equals to LQ is 12 divided by tan 53 degrees. Therefore, we get 12, where is that? 12 divided by tan 53. We get 9,0204. Sorry, 9,04, which is not correct, which is incorrect. We give it a wrong, sorry, an incorrect. This is an incorrect answer because of not being given the whole OQ. So we can't use trigonometric ratios to solve for this. Now, what we need to do here in this problem, we need to use Pythagoras theorem. We already know that angle L1 plus angle L2 is 90 degrees. Now, we can use Pythagoras theorem here. But now for the first thing that I'm going to do is that OQ, which is OQ, is equals to 8 plus the radius, because from here to here is the radius. Then from here to there, because we're given that MQ is 8, therefore 8 plus the radius. This is OQ. OQ is 8 plus the radius there. Now, obviously we do have LQ. LQ is equals to 12. We do have LO. LO is equals to the radius. Now, since triangle LQO is a right angled triangle, then we can use Pythagoras theorem to solve for the radius. Therefore, the hypotenuse, which is the longest side, OQ squared, is equals to the two shorter sides, the sum of the two shorter sides, which is Pythagoras theorem, which is the sum of the two shorter sides, LQ squared, plus LO squared. This is Pythagoras. Now, why are we saying this? The reason is that triangle LQO is right angled. Now, what is OQ? It's 8 plus R all squared, which is equals to what is LQ? LQ, it is 12 all squared, plus what is LO? It is R squared. Now here, obviously, we're going to open two brackets where we are going to have 8 plus R. I just want to show 8 plus R, which is equals to 144 plus R squared. This times this is 64, plus this times that is going to be 8R plus 8R, which is going to be 16R plus R squared. We know this times this is 64. This times that is plus R, 8R plus 8R. This times this is 64. This times that is 8R. This times that is 8R. This times that plus R squared. That is why here I've got 16R, which is equals to 144 plus R squared. Now, R squared and R squared will cancel each other. This cancels that. This goes, that side is going to be 16R, which is equals to 144 minus 64, which is equals to 80. Divide by 16, divide by 16, R is equals to 5. Therefore, our radius is equals to 5. Then we can see that this problem, we cannot use trigonometric ratios, because when we use trigonometric ratios, we're going to get our radius to be equals to 9.04. I'm not sure. Now let's look at another example. Here we are told that tangent KT, which is this tangent, is a tangent at K. This tangent is parallel to that, to n chord NM. Let's start again. We are told that tangent KT at K is parallel to chord NM. And we are also told that NT cuts the circle at L. We are also told that triangle KML is drawn. Obviously it is drawn. Then we are told that angle M2 is equals to 40 degrees. Now, we are also given that angle KT is 84 degrees. This angle here is 84 degrees. That's what we are given. Now, we know our tradition is to eliminate the theorems which are not in the problem before we can even attempt to answer these problems. Because as we eliminate, it helps also to start solving the problem. Now, we eliminate the theorems which are not here. Are there chords? Yes, they are chords. Are there cyclic chords? We are never told of any cyclic chord here. Therefore, no cyclic chord. Are there tangents? Yes, there are. Now, can we eliminate theorems which are for chords? Yes, we can. Is there a line from the center? We are not told of any center in this problem here. Therefore, already theorem number 1, it's out. If we are not told of any center, therefore theorem number 1, theorem number 2 are out, because theorem number 1, it's a line drawn from the center, or theorem number 2, angle at the center, so there's no theorem number 1, no theorem number 2 there. Is there theorem number 3? No diameter, we can't assume that Km is a diameter, we are not told that. So there's no diameter, theorem number 3 is out. Theorem number 4, angles at the same segment. Yes, we do have angles at the same segment here. Therefore, T4. Sometimes we are going to use a theorem there. Sometimes we find that we've got many theorems in a problem, but we use a few. Or sometimes we don't use those theorems. Now, there is angles at the same segment, which is theorem number 4 is there in the problem. Therefore, cyclic chords theorems are out. Theorem number 5 and 6 are out. Theorem number 7, which is a radius and a tangent, there's no radius because there's no center. There's no diameter as well. Therefore, there's no radius perpendicular to the tangent. Therefore, theorem number 7 is out. Now, we can't be tempted that NT is a tangent. So tangent from the same point. No, we can't. So you can see this is not a tangent. It's a chord which is produced at T. Therefore, we don't have theorem number 8 here. We've got only one tangent. So we don't have theorem number 8 here. Therefore, we don't have theorem number 8 here. Now, theorem number 9, we do have theorem number 9 because we do have a chord making an angle with a tangent. Therefore, which is going to be equals to an angle which is in the alternate segment. Therefore, theorem number 9 is there. Therefore, in this problem, we've got theorem number 4 and theorem number 9. And we're also going to use what we have learned in part 1. Now, they want us to find angle K2. Already, I can see that K2 is an angle which is made by the chord and the tangent. Therefore, theorem number 9 in this case. Therefore, it means that this angle there is equal to this angle in the alternate segment because this angle is subtended by this chord, which makes an angle with the tangent. Therefore, this angle, not the whole, but this angle is equals to that angle. Therefore, angle K2 is equals to angle M2, which is equals to 40 degrees. Why? Tan chord theorem. This angle is equals to that angle. Tan chord theorem. Now, we are told to find angle N1. We know that angle N1 is equals to angle K1. Theorem number 4. Angles at the same segment. This angle and this angle here and this angle here, they are subtended by the same chord, which is ML. They are in the same segment. N1 and K1 are in the same segment because they're subtended by the same chord, or they're subtended by this arc there. Therefore, angle N1 is equals to angle K, angle K1. Reason? Angles at the same segment. Now, K1 we can find because we do have the whole of this angle. We also have this angle there. Therefore, this angle minus this angle, we are going to get angle K1. We are going to get angle K1, which is equals to angle N. Therefore, angle N1, which is equal to angle K1, which is equals to M angle K T minus angle K2. I've just said it, that angle K1 is equals to the whole of this angle, which is M angle KT, the whole of this angle, M angle KT, minus this angle, we are going to get this angle, which is K1, which is equals to N1. Therefore, here we have 84 degrees minus our 40 degrees, which is angle K2, 40 degrees, which is 44 degrees. Now, we are also told to find this angle, which is angle T, and knowing that we have just used theorem 4 and theorem 9, we can use theorem 4 and 9 now because angle T is outside the circle. But then we can use what we have learned in part 1, where we were told that this tangent is parallel to the chord NM. Therefore, it means that there's a N shape here. There's my N. There's my N. You can see my N there, or my Z, where this angle is equals to that angle there. Therefore, angle T is equal to angle N1. I'm just going to write that here. Angle T is equals to angle N1, which is equals to N1. We've just said it, that it is equals to 44. Therefore, this is 44 degrees. Reason? Interior, because they are alternating in an N shape or in a Z shape. We've got alternating angles. This angle alternate with this one. Interior, alternate angles. Why are they alternating? Because KT is parallel to NM. Now we do have angle T. Now we can find L2. L2 is this angle there. Just going to highlight it with red. It's this angle there, L2. Now, L2 is equals to the exterior. You can see the exterior angle of triangle KTM. So the exterior angle of triangle KTL is equals to the sum, the exterior angle is equals to the sum of this and that. And we do have K2, we do have angle T. Therefore, we can find L2. Now, I find L2, I'm just going to write this T there. Angle L2 is equals to angle K2 plus angle T. Exterior angle of a triangle is equals to the sum of the opposite interior angle. Reason, exterior angle of triangle what? Triangle LTK. Exterior angle of triangle LTK is equals to the sum of opposite interior angles. Now, we know we are looking for L2. We know K2, our K2 is 40 degrees. Plus, we've just got our angle T, which is equals to N, which is equals to 44 degrees, which you have 40 plus 44, which is 84 degrees. I'm just going to write this plus nicely there. Right, now, we are also told to find L1. And L1 is this angle there. L1 is this angle, which I'm going to highlight in blue. Our L1, we can find using triangle MLK. Because if I add this, plus this, plus this, plus that, which is K1, I'm going to get 180 degrees, sum of angles on a triangle, because we were told that triangle MLK is drawn. Therefore, we can find L1. Now, for us to find L1, for me to find L1, I can say angle L1 plus angle L2, L1 plus L2 plus angle K1, plus angle M2 is equal to 180 degrees. Reason, sum of angles on triangle. Which triangle is that? MLK. MLK. Now, we know we are looking for L1 plus our L2. We have found our L2 to be 84. So I'm looking for L1. L2 is 84. K1, it's 44, which is 44 degrees, plus M2, which is 40 degrees, which is equals to 180 degrees. Now, this plus that, so this is 84 plus 84, which is 168, I think. Angle L1 plus 168 degrees, which is equals to 180 degrees. Now, angle L1 is equal to 280 degrees minus 168 degrees, which is equals to 12 degrees, my L1, which is equals to 12 degrees. I think we have got all the angles that we are looking for by using theorem number 4 and theorem number 9 and what we have learned in part 1. I think now geometry, it becomes easier if you eliminate theorems which are not in a problem, then use what we have learned in part 1. I think now we are just going to look at one last example, because this example is very important, because it's unclear whether we are given a cyclic quad or not in that particular problem that we are going to do just now. But we will tell you exactly why we are given the cyclic quad in that problem. Thank you.